morning, students. I am Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. My topic of discussion is memoryless property of exponential distribution. Let us recap the definition of density function of an exponential distribution. Let us consider the random variate X. Let us consider the random variate which is following exponential distribution. Then its density function is given as f of x is equal to lambda into e power minus lambda x greater than or equal to 0, where x is always treated as time and time is never negative, and hence we always assume x is positive, and this is the density function of the exponential distribution. And if we calculate the distributive function, that is the cumulant probability distributive function, cumulant probability distributive function of exponential function, the result will be like this. First, let us start with the definition f of x. The probability of x less than or equal to x. It means we are calculating all the probabilities, sum of all probabilities. We can assume in the discrete case, it is nothing but sum of all probabilities which are less than or equal to x. Okay, so sum of all probabilities which are less than or equal to x. This is called this f of x. In the continuous case, it could be understood as minus infinity to x f of x dx. That means the sum of all probabilities which are less than or equal to x. Okay, so hence we have written the formula for this minus infinity to x f of x dx, which turns into 0 to x f of x dx. Why minus infinity turned to 0? Just answer yourself. Why minus infinity turned into 0? Simple reason, I already told you that f of x is a exponential distribution, then x is always non-negative as time is always positive. So automatically that as per the domain, it minus infinity turns into 0, 0 to x f of x dx. And what is f of x? Just let us question answers. In the exponential distribution, f of x is lambda into e power minus lambda x. So this integral becomes lambda into e power minus lambda x, which is like this. And you know lambda is a constant, it can be written out. And you know integration of e power ax is e power ax by a, and hence we get e power minus lambda x by minus lambda under the limit 0 to x. And by substituting the limits, we finally arrive at the answer 1 minus e power minus lambda x. So we have derived that the distributive function of exponential distribution is 1 minus e power minus lambda x. Okay, now what is the use of distributive function and how it differs from the density function? We have two functions, f of x, f of x. This is density function and this is distributive function. What is the difference between these two? These two are two different calculators of probabilities. This is a calculator of probability. In a vague sense, you can understand as this is a calculator of probability, and this is also a calculator of probability. Then why we need two different calculators for the same calculation of probability? This calculator helps you to calculate the probability point-wise. That is, what is the probability of happening of an event at the exact xth minute. This is probability of happening an event at exact xth minute. That is the probability. But this is cumulative. That is, what is the probability of happening an event within x minutes, less than or equal to x minutes. That means f of 10 means what is the probability that an event is going to happen exactly at 10th minute from now, exactly at 10th minute. But this is what is the probability f of 10 means probability of happening an event less than or equal to 10 minutes, that is within 10 minutes. This is within 10 minutes. This is exactly 10th minute. So that is the difference between these two calculators. And both calculators can be used to calculate probabilities. It depends on the situation and the requirement of the problem. So the summary, that is f of x, is understood as 0 when x is negative and 1 minus e power minus lambda x when x is positive. And uh, let us recap what is the expectation of exponential distribution. You know, every random variate, whether it is discrete or continuous, will have two parameters, namely the expectation and the variance. These two play a very vital role in determining the probabilities. Here, expectation, the exponential distribution, will also have e of x and b of x. If you see the e of x derivation, it runs like this: integral 0 to infinity f of x d. Actually, let us recap the definition of e of x, that is x into f of x d of x. This is the exact formula which we learned in probability and statistics course in second semester. So by using this definition, we will substitute f of x as lambda into e power minus lambda x. And lambda being constant, it can be written outside. We'll use Leibniz rule. By using Leibniz rule, it is a polynomial which we discussed in the last class. The integral becomes x into e power minus lambda x by minus lambda minus 1 into e power minus lambda x by minus lambda whole square under the limits 0 to infinity. By using the Leibniz rule, we can immediately write this integral by using the Leibniz rule. Okay, and by substituting the limits, we observe that the value becomes lambda into 1 by lambda square, and hence we get expectation as 1 by lambda. And also, in the same way, we could prove e of x square is 2 by lambda square. And variance of x. Of course, we have discussed these derivations in the last class. You can refer to the previous videos for these derivations. V of x is nothing but e of x square minus e of x. So 2 by lambda square minus 1 by lambda square, that is 1 by lambda square. So these are the two important parameters which we are going to use in determining probabilities as well as the memoryless property. So finally, let us write the formula once. E of x is 1 by lambda for exponential distribution and variance is 1 by lambda square. Now, let us look into the important aspect of exponential distribution, that is memoryless property. Statement runs like this: for a random variate which follows exponential distribution and for any two positive real numbers x and y, probability of x greater than or equal to x plus y, given that x greater than or equal to x is equal to probability of x greater than or equal to y, that is probability of x happening after x plus y minutes, given already x minutes completed, given already x minutes completed is as equal as the probability that the given task will be completed after y minutes. After y minutes. That means this memoryless property states that if you assume that it takes at least 10 minutes to complete a task, suppose it takes at least 10 minutes to complete my video lecture. Suppose I'm assuming that it takes at least 40 minutes to complete my video lecture. Okay, already I have completed 20 minutes of the lecture in the yesterday. Suppose 20 minutes of the lecture has been delivered yesterday, so that is x greater than or equal to 20. That means the remaining, that is suppose 15 minutes, let us assume that 15 minutes of the lecture has been completed yesterday. Then what is the difference? 40 and 15, that is 25 minutes. So this is equals to the probability of x greater than or equal to 25. So the condition probability that probability of x greater than or equal to 40, given that already 15 minutes completed, is equals to the remaining gap, that is probability of x greater than or equal to 20. A task which is supposed to be completed at least 40 minutes, given that already 15 minutes of work is done, then it is the probability will be equal to, automatically will be equal to the task will be completed at least 25 minutes. That is 40 minus 50. Okay, this is what we call memoryless property. This helps us to calculate the probability quickly when the time bound is very high under exponential distribution. So let us look into the proof of this property, and then we'll see some applications of memoryless property. So let us start the proof. This is the LHS. That is the probability of x greater than or equal to x plus y, given that already x minutes are completed. We are assuming that it takes x plus y minutes for us to complete the task. But already x minutes work is already done. Okay, and we have to show that this is equals to p of x greater than or equal to y. Okay, so we have to arrive at this. So for that, let us take the LHS. Let us start with the LHS. Now, this is a conditional probability. Let me explain this proof in an easy way. Probability of x greater than or equal to x plus y, given that x greater than or equal to x. You know what is P of A by B formula that you have come across in your second semester curriculum? The probability of A given B is nothing but probability of A intersection B given probability of B over probability of B. This is called conditional probability of an event confining to the condition B is already had. So you know this formula very well. So by using that, we can write it as probability of x greater than or equal to x plus y intersection x greater than or equal to x, given p of x greater than or equal to x. That means we are taking this as A and this as B. So A intersection B by P of B. So we have arrived at this step by using this definition. By using this definition, we have arrived at this step. Now clearly, we can easily understand the common sense that whatever element in this set will be in this set. That means whatever an event which takes at least x plus 5 minutes, that means it automatically crosses x minutes. That means the set x greater than or equal to x plus y is subset to x greater than or equal to x. Because suppose this is 20 minutes, this is 6 minutes. Automatically, if you need a task, if you need at least 20 minutes to complete a task, that means you need at least 6 minutes to complete that task. So automatically, this set will be a subset of this set. So here we could understand it as P of intersection always goes to the subset. We can write it as x greater than or equal to x plus y by P of x greater than or equal to x. That is what we have written here. This is subset. This set is subset to this. You know, when A is subset to B, A intersection B will be equal to A. That is what this is subset to this, and hence this intersection becomes x greater than or equal to x plus y. Now let us recap the definition of exponential distribution. By using that, this becomes x greater than or equal to x plus y becomes e power minus lambda of x plus y. Okay, and p of x greater than or equal to x becomes e power minus lambda x. Simple. Let me explain the reason how this step has been attained from the above step. See, you can write it as by using the cumulative distributive function 1 minus x less than or equal to x plus y, and also this can be x greater than or equal to, so this can be also written as 1 minus f of x less than or equal to x, and this is 1 minus lambda into 1 minus 1 minus lambda into e power minus lambda of x plus y, and this is 1 minus 1 minus lambda into e power minus lambda x. So automatically this becomes lambda into e power minus lambda of x plus y over lambda into e power minus lambda x, and lambda can be cancelled, and hence we get this step. And by multiplying lambda with x and lambda with y, you can write it as e power minus lambda x into e power minus lambda y over e power minus lambda x. Automatically this will be cancelled, and we arrive at e power minus lambda y, which can be written as 1 minus e power lambda y, which can be written as 1 minus f of x less than or equal to y, which is nothing but 1 minus p of x less than or equal to y, which is nothing but p of x greater than or equal to y. Okay, so this is the way we prove the memoryless property of exponential distribution. So finally, what we understood is p of x greater than or equal to x plus y, given that already x minutes completed, will always be equal to probability of x greater than or equal to y. This is called memoryless property of exponential distribution. Now, let us look into the applications of memoryless property. Suppose that the longevity of a light bulb is exponential with a mean lifetime of 8 years. Here he is clearly mentioning that it is the lifetime of a light bulb is following exponential distribution. So what can you assume? You can assume that the density function will be lambda into e power minus lambda x, and capital F of x will be 1 minus e power minus lambda x. Now come to this line. Mean lifetime of a light bulb is 8 years. That means what is the mean of exponential distribution? We have already found that the mean is 1 by lambda. So 1 by lambda is equal to 8 years, and hence lambda is equal to 1 by 8. And if a bulb has already lasted for 12 years, already we bought a bulb of that company, and it has been working since 12 years, already completed 12 years lifetime, then find the probability that it will last a total of over 19 years. Over 19, that means the bulb will sustain more than 19 years. The lifetime of the bulb should exceed 19 years. Okay, given that already 12 years it has completed its life. Okay, let us find out the solution of this problem by using memoryless property. So according to the data, lambda is equal to 1 by 8, as 1 by lambda is 8, and according to data we have to find probability of the lifetime exceeding 19 years, given that probability already the bulb has completed 12 years. How could I write this? See here, over you can translate it into mathematics as greater than or equal to. So over 19 years means greater than or equal to 90. That is why I have written this. And given that, why I have written condition here? Already he is stating that the bulb has already lasted for 12 years. So this is we have to obey this condition that bulb has already have lifetime of 12 years, and we are expecting that it will cross over 19 years. That is what we are asked to find. So according to the memoryless property, this will be equal to x greater than or equal to 7. Because I already told you the difference 19 minus 12 is 7. According to the memoryless property, automatically this conditional probability will be equal to the direct probability that x greater than or equal to 7. So that is 1 minus p of x less than or equal to 7. Okay, you might be surprised. Sir, actually it is greater than or equal to. You have to put only strictly less than, but you are using less than or equal to. Will it matter? It doesn't matter because it is a continuous random variate. In continuous random variate, the inclusion of equality or deletion of equality won't matter because if you have an amount of crores of money, if you subtract 7 rupees or adding 7 rupees won't doesn't change the value of the money because it is a huge lump sum amount. So it won't be a problem with the inequality sign. So let us write the distributive formula, that is 1 minus e power minus lambda of 7, because we already learned that if p of x less than or equal to 7 will be equal to the formula 1 minus e power minus lambda x if it is x. So by using that formula, we have written this. So that is e power minus lambda means 1 by 8 into 7. And the final answer is e power minus 7 by 8. If you calculate this value by using your calculator, you will get the probability that the bulb will last more than 19 years. Of course, it has already completed 12 years of lifetime. Let us look into the solution once again with the help of the PPT. Next slide. So clearly, according to the data, lambda is 1 by 8. That is what I have written here in the first line. And according to the cumulative formula, p of x less than or equal to x is 1 minus e power minus lambda x. That is 1 minus e power minus t by 8. Now, according, we have to find this probability because we are already assuming that 12 years are completed, and what is the probability that the bulb will cross over 19 years. So automatically, according to memoryless property, this probability will be equal to p of x greater than or equal to, or t greater than or equal to 7. That is the difference of 19 and 12. That is what I have written here. And by using the complementary probability, this equals to 1 minus p of t less than 7. And according to this formula, we can write p of t less than 7 as 1 minus e power minus 7 by 8. And e power minus 7 by 8, which is equal to 0.4169, which tells you that there is a 42% approximate of chance that the bulb will last for 19 years, more than 19 years, uh, to be sustained over than 19 years. Okay, and let us look into another application of a memoryless property of exponential distribution. The time a postal clerk spends with his or her customer has an exponential distribution with a mean of 4 minutes. So here he is clearly mentioning that x follows exponential distribution. And also he has given that mean of 4 minutes. What is the mean of exponential distribution? That is 1 by lambda. 1 by lambda is 4, and hence lambda is 1 by 4. Let us look into the meaning of the question. The time of a post clerk spends with his customer. That means when a customer arrives to the post clerk, has to supply the stamp, has to check the weight of the cover, and accordingly has to supply the stamp. And after stamping, he has to collect the cover, and again he has to tag that. He had to tag that with the correct slip of address, and has to note it in the system, and he has to return he has to give a slip of acknowledgement to the customer. So for this, generally, postal clerk takes on an average 4 minutes for each customer. If you go to the post office and if you ask for speed post or register post, it takes 4 minutes of time to complete the process. Okay, basing on this record, we are supposed to calculate a customer already has spent 4 minutes with a post clerk. Already he went there. A customer went there for a speed post or register post. He already spent 4 minutes, but still the work has not done because there is a queue. There is a queue, or there is a system problem or computer problem. So it is taking time. What is the probability that she has to spend at least an additional 3 minutes with the post clerk? What is the probability that she has to spend additional 3 minutes with the post clerk? That is the question. Okay, so let us let us take down the important details from the data. That is, lambda is equal to 1 by 4 because mean is 4 minutes, and we have to find the probability that has already spent how many minutes. Already spent 4 minutes, so already spent 4 minutes. What is the probability that he has to spend additional 3 minutes? That means 4 plus 3, that is 7 minutes. This is equal to additional 3 minutes, that is greater than or equal to 3. Okay, so when we look at this, we can write the complementary probability 1 minus p of x less than 3 or less than or equal to 3. Okay, and by using the distributive function, this becomes 1 minus e power lambda of 3. 1 minus 1 minus e power minus 3 by 4. That is e power minus 3 by 4. And if you calculate, this will be approximately equal to almost 0.45 or like that. That means there is a 45% of chance for that the customer has to spend more 3 minutes to complete his process of registering the post. Okay, so this is how we can apply Memoryless property to find out a realistic or real-time probabilities related to time. Okay, and let us look into one more application. The lifetime of an electric component is a continuous random variate with a probability density function given by f of t is equal to e power minus t. So here, electric components, there are so many electric components that we come across in our life. So you can see the examples in this diagram. Okay, these are so many. These are the you can see various kinds of electric components. Okay, and the lifetime of this electric component manufactured by a branded company is follows exponential distribution where f of t is e power minus t. Okay, uh, that means the probability that the component will last for 1 year is f of 1, that is e power minus. The component will have a lifetime of 2 years, will be e power minus 2. That is what it is stating. The exponential distribution means f of x is equal to lambda into e power minus lambda x. By comparing lambda e power minus lambda x or lambda t with e power minus t, we immediately conclude that lambda is equal to 1. That is what he is mentioning here. Okay, we can easily understand that lambda is 1. Now find the lifetime with a typical component is 60% certain to exceed. If 5 components are sold to manufacture, find the probability that at least one of them will have a lifetime less than n years. This is a typical application of exponential distribution. Let's try to understand what he's asking in the question, and let us discuss how to find out the solution. So, according to the data, it is clear that the function is f of t is equal to e power minus t, where lambda is 1. This is very important thing. Lambda is 1. Okay, and find the lifetime L with a typical component is 60% certain to exceed. That is, we have to find that the lifetime exceeding some x naught year, suppose an electric component we purchase of that company will last for x naught years at least, is 60%. We have to find what is x naught. We have to find the value of x naught, assuming that the component lifetime will be over than x naught years is equals to 60%. So according to the formula, the formula is 1 minus e power minus lambda x naught is 60%. That is 0.60. 60. So e power minus x naught, because lambda is 1. Lambda is 1, we can write it as e power minus x naught is equal to 0.4. So e power minus x naught is equal to 4 means minus x naught will be ln 4, logarithm of 4, because when we apply log on both sides it becomes minus x naught will be equal to logarithm of 4. And by using logarithm tables or calculator, you can find what is the value of x naught. That gives you how many years it takes, so that the component lifetime will exceed x naught years is 60%. Okay, and let us go to the second bit. If 5 components are sold to the manufacturer, find the probability that at least one of them will have a lifetime less than L years. Okay, that means we have to find probability of x less than or equal to L years. Okay, for 5 components. P of x greater than or equal to L means 1 minus e power minus lambda L. And lambda is 1 from the data itself. We can find lambda is 1, that is 1 minus e power minus. This is for one component. How many components we are purchasing? 5 components. That means it has to be multiplied with 5. 5 into 1 minus e power minus L. So in this way, we can calculate probabilities by using exponential distributions in the real time. Now, let us see one more important application. With this, I'd like to conclude the lecture with this application. Commonly, car cooling systems are controlled by electrically driven fans, assuming the lifetime T in hours of a particular make of a fan can be modeled by an exponential distribution with lambda is equal to 0.0003. To cool the car engines, we use cooling systems. The cooling systems will be designed which are controlled by electrically driven fans, the battery driven fans. You can see here there are 2 fans which help you to cool the system, whether it is engine or inside the car. We'll use some electric fan kind of electrically driven fans to cool the system. And the lifetime of these fans will follow exponential distribution with the lambda value 0.0003. So he is stating that the lifetime of these fans is exponential distribution with the function f of x is equal to lambda into e power minus lambda x, where lambda is equal to 0.0003. Now, find the proportion of fans which will give at least 10,000 hours service. That means the fans will last up to 10,000 hours. Okay. So what is the probability? What is the proportion of such kinds of fans? Okay. Or probability of fan. Proportion and probability both are synonyms in terms of probability. So we have to find P of x greater than or equal to 10,000 hours. Okay, and this is 1 minus e power minus lambda x formula, that is 1 minus e power minus 0.0003 into 10,000. Okay, that means you can write it as 3 by 4 zeros and you can cancel, you will get 1 minus e power minus 3, and hence you can find out the probability that the proportion of fans which will give at least 10,000 hours service. Okay. And also we are asked to find if the fan is redesigned so that the lifetime may be modeled by exponential distribution with 0.0003. That means we are improving the technology. We have improved the technology and we have increased the rate of increment of life with 0. Initially it is 0.0003, but now we are with the improved technology, the rate of increment of life is raised to 0.00035. Okay, that means initially it is 0.0003, 0.003%. Now it is raised to 0.0035%. There is slight increment. So with this probability again, if we suppose to calculate the probability of lifetime will exceed the probability of lifetime of the electrical fans will exceed 10,000 hours. Okay, that will be 1 minus e power minus lambda x, that is 1 minus e power minus 0.00035 into 10,000. So automatically it will be e power minus 1 minus e power 3.5. Okay, so by calculating this, you will attain the probability, and hence we can assume that exponential distribution always increasing with time to time. So yes, yes, the same problem here. I'm going to explain with another new diagram. Here you can see an electric fan which is cooling the engine. This is a car, and this is the engine in front of the car. And here you can find an electrical cooling fan. Okay, the lifetime of fan determines the lifetime of engine, and this is follows an exponential distribution 0.003. That is what given in the question. Okay, so like this. Now, finally, I'm going to give a recent example, very recently happened example of which can be modeled with exponential distribution. You can see a ship. Do you identify this? Can you identify this ship? It is nothing but the ship which is struck in the Suez Canal a month ago. It took almost 9 days to to control the traffic and again to make the ship into the correct way, because it was blocked all the traffic by stucking in the middle of the Suez Canal. Here such kind of problem has been modeled by exponential distribution. The time intervals between successive batches passing a certain point on a busy waterway. Busy waterway means you can assume a Suez Canal like that. Okay, it is very busy in the Suez Canal. Always there will be ships moving from one end to the other end, and the width is very less because it is just a canal. You cannot find one ship has to move after other. They should follow an order. Okay, and on an average it takes 8 minutes to pass a certain distance in the Suez Canal. To pass over this way in the Suez Canal, it takes at least 8 minutes. Suppose when we are moving on our bike, it takes at least 8 minutes to cross over what do you call um, in a highway. In a highway, what is that? Yeah, in a highway, the toll plaza. Yes, toll plaza. Suppose sometimes you may have to spend 8 minutes on an highway. That kind of situation has been explained over here. Find the probability that the time interval between two successive batches is less than 5 minutes. In this case, you have to find that the probability of the time spent by two successive batches. That means two ships to go through the toll plaza will be less than or equal to 5 minutes. Okay, this can be calculated with the help of the formula lambda of 5. And find the time interval t such that we can have 95% surety that the time interval between two successive batches will be greater than or equal to t. That is, p of x greater than or equal to t will be 95%, that is 0.95, that is 1 minus e power lambda t is equal to 0.95, where we have 1 by lambda is equal to 8 minutes from the question. Lambda is equal to 1 by 8, and hence this will be equal to 0.05 is equal to e power minus t by 8, and t is equal to, and t minus t by 8 is equal to log 0.05, and minus t is equals to 8 into log 0.05, and you can calculate this value by using the calculate, and you can determine how long it takes to have 95% surety that it will take more than t hours to t minutes to complete the crossover. Okay, in this way you can understand applications of exponential distribution and memoryless property. With this, I'd like to conclude my lecture, and in the next lecture we'll start the third module of the curriculum, that is probabilistic modeling and reasoning. Thank you for your patience listening. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.